Okay. All right. Okay, so we're going to discuss NP-completeness and what it is that NP means. We started this last lecture on the definition of NP. Let me, so it takes, okay. So the motivation to consider this class of problems is that there are many natural examples, and some of these are what we discussed already: independent set, vertex cover, set cover, which we didn't discuss, SAT, 3-SAT, for which we have simple exponential time algorithms by brute force, but for which we don't have any efficient polynomial time algorithms. So how do we deal with them? And one of the features that they have, which I'll formalize, is that like Sudoku, right, that they all have the feature that if we are given a solution, it's easy to check that it's actually a valid solution, right? So if I give you a solution to a Sudoku puzzle, it's that satisfies all the constraints that I want, right? And that's one property, that given an instance of the problem and the solution, we can easily check, right, that it's actually a valid solution. The second part, which also I discussed last time, is that the size of the solution is not too long compared to the size of the problem instance itself. And that might seem like an obvious property, but it's not, and I'll give you an example to show you that it's not true for all problems that we may encounter. Okay, so those two properties are fairly common in many problems that we encounter, right? That if you give a problem and a solution, it's easy to check that it's a valid solution, and two, that the solution size is not too long compared to the instance of the problem itself, right? Those are important properties that hold true for many problems, and collectively those are what are called NP problems, right? So let me formalize this so that we can actually have a formal definition of what NP is, right? The two ways of defining NP, one is actually the more, I think, if you had time, that's probably the right way, not right way, that's one important way, is to define it as non-deterministic polynomial time algorithms via Turing machines, okay? Because then it's actually very technically clear, and it's easy to prove the Cook-Levin Theorem formally and so on. But that will take some time to develop, but this is equivalent, except there's slight fuzziness when you kind of really want to pin down some details, okay? So, because there is always fuzziness in the definition of an algorithm, right? When you think of it as an algorithm, there's always a bit of fuzziness on what operations are allowed and so on, while the important thing about Turing machines is that there's no fuzziness. On the other hand, the problem is that Turing machines are so simple that it's very hard to program in them, right? So there's a balance, but in the interest of time and also this interest of high-level thinking, we'll just stick with this definition, right? Okay, so we're going to formalize this notion of efficient checkability, right? What does it mean, that efficient checkability, right? So first we'll define this funny type of algorithm called a certifier, right? A certifier or a verifier sometimes is simply an algorithm that checks a solution, right? Okay, so what does it mean to check a solution? So a verifier is an algorithm which takes two inputs, not one, right? Normally when you want an algorithm, what do you want? We just want to give an instance of the problem, we want to solve it, right? Here it's a verifier, it is not actually solving the problem. All it is doing is actually going to check the solution, right? But checking the solution means that not only do I need to have the problem, but I also need to have a solution to check, right? So this algorithm takes two inputs, an instance of a problem and say solution or a proof, right? So a certifier is an algorithm which takes two inputs, and it is a certifier for a problem X if it has the following property, right? For every input instance S of X, if it is a, remember X is a decision problem, right? Okay, so what does it mean X is a decision problem or a language? Some instances are yes and some instances are no, right? Yeah? Okay, if the instance has a yes answer, like a Sudoku puzzle, the answer is yes, it must have the property that there is some string t, which is a solution or a proof, such that the verifier will say yes. Okay? The verifier takes both the instance, like the Sudoku puzzle, and a solution, and it will say yes if it is indeed a valid solution. Okay? Okay? If the instance is not a yes instance, what does that mean? That suppose the Sudoku puzzle doesn't have a solution, the verifier should have the property that whatever solution you give it, it will say no. Which makes sense, right? We don't want to, I mean, if the puzzle doesn't have a solution, the verifier should have the property that if you give it some random thing and say, oh yes, see, this is a, I mean, at the minimum we want the verifier to have the property that if the puzzle doesn't have a solution, it shouldn't get fooled. Yeah? So that's what a verifier is, right? A verifier takes both sort of like a puzzle or an instance of a problem, and if the answer is yes, you can convince it by giving it a valid proof. It will check, yes, yeah, this is a valid solution, yes. Okay? And if the answer is no for that instance, whatever proof you give, it will say no. Okay? Does it make sense? What a verifier does? It's just verifying, checking whether the solution is correct or not. Okay? Questions? Yeah? This seems all right? Okay? Okay. But we don't want it just to be just a verifier, we also want it to be efficient, right? Okay. A verifier is an efficient verifier or a certifier if first it runs in polynomial time, right? The verification should happen in polynomial time, right? Given a input and the proof, it shouldn't take a huge amount of time to actually verify. It should take polynomial time in the length of the puzzle and the solution. Yeah? That's an efficient verifier. And moreover, we want the additional property that if the answer is yes, the length of the proof is actually only polynomial in the size of the input instance. Okay, this is the property I was saying, right? So here is so there exists some polynomial p such that the length of the proof to convince the verifier should be polynomial in the input size. So for example, in the Sudoku puzzle, what are we going to give the verifier? We're going to fill all the blanks, right? The size of the blank filling should be polynomial in the size of the original puzzle, which is trivially true in the Sudoku case. But you can imagine problems for which that's not always true, right? That the proof to convince me about something is correct could be much longer than the original statement, right? Yeah? So that's not in our purview, right? We say a problem has an efficient verifier if it has an algorithm with two inputs, right? It takes the instance and a proof and a short proof. So that what is the length of the proof? It should be polynomial in the size of the input instance. Okay, therefore there's a fixed polynomial p. And the verifier also has to run efficiently in polynomial time. Yeah? Okay. So okay. And examples. So take the graph independent set problem. What is the independent set problem? I have a graph and an integer k, and does this graph have an independent set of size k? Okay. What is a certifier or a verifier for it? Well, what should we do? I mean, it's very intuitive, right? My verifier expects what? If I want to be convinced that this graph has an independent set of size k, it expects a set of vertices, right? And what can it do? It will check first. You give me a set of vertices and it will say, okay, is this set of vertices actually an independent set? It can check, right, easily. Are there any edges between any two vertices in this set? And moreover, is a set size at least k. If those two properties are true, it will say yes. Otherwise, it will say no. Yeah? Yeah, it's very efficient to check whether a set of vertices have any edge between them, right? It's polynomial time. And the proof size. What is the proof size to convince the verifier that there is an independent set of size k? It's simply a list of vertices, right? It's not much longer than the size of the graph, right? Given a graph and a vertex set k, if the answer is yes, the size of the proof to convince the verifier is only the list of vertices at most of size n, right? So the length of the proof is actually not much larger than the size of the graph itself. Yeah? So you agree that the independent set has an efficient verifier? Yes? Yeah? Any questions on that? Yeah, so I mean, remember verifier means it cannot solve the problem itself, okay? But it takes two inputs. What is its input for this problem? A graph and k, right? And if you give it a proof, I mean, see, it takes two inputs, right? It's only verifying solutions. So what should it have? It should have the property that if the graph indeed has an independent set of size k, there should be some proof or a certificate that will convince that it's true. Okay, I mean, let's think informally. How will you convince me that the graph has an independent set of size k? If you believe it, the graph has it. You want to convince me I'm a slow verifier, right? I can only do polynomial time computation, right? I can't find the independent set by myself. But if you give me a set of vertices and see, look, this set has size k and this is the set that will convince me. I can check, right? Oh, does this set actually, is it an independent set of size k? That's easy, right? Because first I can go and say, are there k vertices in the set, right? And second, I can check, is there any edge in the graph between any two vertices? If there isn't, then I know that this graph has an independent set of size k. Right? The algorithm to check is much easier than actually finding the independent set. Right? So what we are saying is that the certifier takes two inputs, the graph k and a set. Right? But suppose the graph doesn't have an independent set of size k. You cannot fool me, right? Whatever set you give me, if it is not an independent set, I will say no. Right? Whatever set you give me, not independent set, whatever set you give me, if it is not an independent set of size k, I will say no. It's a weird concept, right? A little bit, right? But we are saying, you may think that it's completely obvious, every problem should have this property. But it's not true, right? Not every problem will have this simple property, right? It's a property of the problem. That's the important thing to understand, right? Okay, we'll get the hang of it. Vertex cover too, right? If I want to convince, there's a simple algorithm such that it can verify vertex cover, right? What does that mean? That if you give it a graph and k and a proof, it will say yes if the graph has a vertex cover of size k, and if it doesn't have a vertex cover of size k, then whatever proof you give, it will say no. Right? You can check. It can't be fooled, right? And moreover, the size of the vertex cover is only size n, right? Not much bigger than the size of the graph, right? Same thing for SAT. How will be a verifier for SAT? You just give it an assignment, right? Yeah. Okay. Good. So all these are good. Okay, let me skip this. But let me give an example where this is not as obvious as it looks, right? Okay. So here is a problem where the problem is given an NFA. Does it accept all strings? Okay. Okay. So now I wanted you to know, is it an NP? Is there an efficient verifier for it? How will you, so it's good to understand this, right? Because it's not obvious now, right? If I give you an NFA and say, does it accept all strings? You have to say yes or no, right? That's the problem, right? Now, we can solve it in exponential time by converting it into a DFA, and then that's easy. Once you have a DFA, it's easy to check whether it accepts all strings, right? How do we do that? We did this last lecture, just to recap. If I give you a DFA and ask, does it accept all strings, how will you verify that? What's an algorithm for that? All the reachable states should be final states, right? All the reachable states from the start state should be final states. So it's easy to do that by graph search if it's a DFA. But for NFA, it is tricky, right? Because for NFA, you can try to convert it into DFA, but that'll take exponential time to convert it into DFA, right? But maybe it's in NP, right? Maybe there is a small, short way of convincing a verifier that it accepts all strings. Can you think of a short way of convincing a verifier that it accepts all strings? Okay, so so that's what I'm saying. It's not obvious that every problem has this nice efficient verifier, right? Convincing that an NFA doesn't accept all strings is not obvious. I'm saying that even that, I mean, even as a verifier, we can't figure out an efficient verifier for it. Okay? All right. So the problems can be tricky, right? All right. So for example, another problem is that I give you two NFAs, NFA1 and NFA2, and I ask, is there intersection empty, the language of their, I mean, are there two NFAs not going to accept any common string, right? That's also very tricky. How will you efficiently verify it, right? It's not easy. So these are universal things and it's not easy, right? Yeah. So okay, so size of the problem and the solution, right? So it's important definition, right? You know, so they both, okay. So in the definition of the efficient certifier, the size of the proof should be polynomial in the size of the input problem, and the algorithm should run in polynomial time as well. In the both is inputs, right? It's input. It's taking two inputs, right? So this combined input is the sum of their lengths. So it should run in polynomial time, and the proof also should be of polynomial time. Okay, both are important. Okay. Okay. So basically, not every problem is in NP. So here is this is very first lecture, post correspondence problem, right? And this is another important thing. I don't know if I have I should have had an example. Maybe I'll pull it up. So post correspondence problem is very simple, innocent sounding problem, right? What is it? I give you two sets of strings, alpha 1, alpha 2, alpha 1 up to alpha n, and beta 1 up to beta n, right? And what is the question? Can you take these strings, align them in such a way that if you take string alpha 1, you have to take string beta 1. If you take string alpha 3, you have to take string beta 3, right? So you want to find a sequence of indices I1, I2, Ik, such that, you know, if I put alpha 1, alpha I1, beta I1, alpha I2, beta I2, and take the concatenation, they should lead to the same string. Okay? So maybe from the first lecture I have actually I forgot to put this in this. Let me see if I have it on my. It's a very simple problem, innocent looking problem, right? Yeah, I have an example. Good thing. Okay, so here is an example, right? So I have basically, it's like a tiling problem, right? You know, I have, so I mean, you can think of, you know, I give you top strings alphas and bottom strings betas, right? Okay. Now, what you need to do is, you know, take these tiles and put them together. You can use the same tile multiple times, such that this string is the same as this string. Yeah. Okay. So in this example, the answer is yes, right? Because I took this tile and okay, you can see the example. It's A B B B A B B A whatever, and it's the same string as top and bottom. Yeah. Is the problem clear? Yeah. So the answer is yes in this case. And you can easily create examples where the answer is no, right? If the top alphabet is completely different from the bottom alphabet, you're not going to get, right? Okay, for some things it will be yes, and for some things it's no, right? Okay, now does it have an efficient verifier? And he said yes, yes, yes. It's very easy to verify, right? Okay. Here is a catch. If I give you the input strings and a solution, it's linear time to verify it, right? Linear time in what? In the size of the original problem and your solution. Yeah? That is, but how are you sure that the size of the solution is small? Okay? Okay, how do you know that the length of this sequence will be small compared to the original input strings when the answer is yes? Okay, that's a very, very fundamental question there, right? If I give you the solution and the original strings, it's very easy to verify that it's actually a solution. Very easy meaning the running time of your verification algorithm is in fact linear in the size of the original strings and the solution, right? It's so easy to check. right? You concatenate the strings and check whether it is actually a solution or not, right? However, there is no guarantee that if there is a solution, the size of the solution will be small in terms of the original strings. That is not obvious at all, right? What guarantee do you have? In fact, you may have to repeat the same tile many times, right? Is that clear? That I could start with these tiles, but any valid solution might need a billion tiles. And you may say, oh, that doesn't seem possible, right? But it is true. In fact, the problem is undecidable. Okay? The problem is undecidable. Okay. What does it mean? The problem is undecidable means that there is actually no algorithm. Forget efficient algorithm. Okay? So it is true. This is an extreme example, right? If in fact I give you a solution, it's so trivial to check that the solution is a valid solution, right? But there is no upper bound on the length of the solution that in terms of the size of the original strings. In fact, it could be unbounded. Okay? All right. So it is not obvious. All I'm saying is that the fact that verification is easy in terms of once you're given the solution doesn't mean that the length of the solution is guaranteed to be small compared to the original input size. Well, that is not true for SAT, right? For a SAT formula, if there is a solution, you're guaranteed that the size of the solution is small, right? It's just a satisfying assignment. Is that clear? Okay, you have to be careful. I'm saying that both parts are important for a definition of NP. One is that the verification should be polynomial in the size of the input and the solution, but also that there exists a solution, if there is one, of short length. What is short? Short in the size of the original input, right, of these strings. But there is no guarantee for this PCP like that. Yeah?
I mean, the solution must be equalist.
No, because I'm allowed to duplicate, right? See, I use the same tile multiple times. Okay, yeah, that's the importance of this problem, that you're allowed to use these tiles more than once. Otherwise what you said is true. Okay, the fact that I'm allowed to use something more than once is what causes trouble. Okay, in fact, using these tiles you can encode any Turing machine computation. That's why it's undecidable. All right, it's a simple string tiling problem is undecidable. If you're not interested in Turing machines, or like it's too abstract, here is a very concrete problem that you can explain to even children, right? Oh, make these tiles and give them a huge number of copies of the tiles and say, can you make the tiles match up, right? You can make children understand this puzzle, right? The thing is, there is no algorithm to solve this puzzle. Okay, it's not exponential time or something. There is no algorithm in the worst case, right? That is, for every puzzle, I'm saying, if you give an arbitrary puzzle, we don't have an algorithm which solves all puzzles, right? So that's the meaning of undecidability. So it's very concrete that way. All right. So okay. Anyway, that's important to understand that size of the solution is not guaranteed to be small compared to the size of the original problem, and this is an extreme example. Okay. Okay. So what is a non-deterministic NP? NP is the set of all problems that have an efficient certifier. Okay? PCP is not in NP, right? Okay? Because it's undecidable, right? So all these problems are in NP, right? Because they have efficient certifier, independent set, vertex cover, set cover, SAT, 3-SAT, composite, all examples of problems in NP. Okay, why is it called non-deterministic polynomial time? Because if you respect to Turing machines, it's exactly the same definition as a certifier. Okay, non-determinism corresponds to guessing that proof, right? Like in NFAs, right? And NFAs guess the proof and then verify it, right? The same thing you can define with Turing machines, but we won't go into that, right? Okay. Okay, why is it called non-deterministic polynomial time? You can do it later. So one important property that I need to mention to you, it's only that NP is a bit funny, right? It's only that the yes instances have a short proof. Okay, take Sudoku puzzle, right? Suppose I want to convince you that the Sudoku puzzle doesn't have a solution. How will you convince me that it doesn't have a solution? Sorry? Yeah, but that's not short proof, right? If you want to convince me that there is no solution, what can you do? You can, is there an efficient verifier for that? It doesn't seem, it's not, it may be, but it's not obvious, right? Because, how will you convince me there is no solution? Yeah? So it's tricky, right? NP is asymmetric in that way, right? NP is saying that for the yes instances, the verifier is efficient and has a short proof, right? For no instances, there is no guarantee, right? Okay, so there's an asymmetry in the definition of NP, right? And so NP is actually not closed under complement. Okay, that means that if a problem is in NP, it doesn't mean the complement is in NP, right? In fact, the complement is called co-NP. Okay, and I won't go into this, but if you have time, we'll see, right? Okay, first observation, right? P is in NP. What does that mean? That if a problem can be solved in polynomial time, then it's trivially in NP. So NP is actually a bigger class. Why is that? So so this is a useful test for us to understand what is NP, in the sense that when does the problem belong to NP? It has a verifier which is actually much weaker requirement than solving it, right? So if I have a polynomial time algorithm for a problem, do I need any help in checking that it is actually yes or no? I don't, right? Because I already have an efficient algorithm for it. I don't need proofs or anything and somebody to help me, right? Suppose you have an efficient algorithm to solve Sudoku, right? Why do you ask your friend for help, right? You won't ask your friend for help, right? If you have an efficient algorithm, you'll do it yourself, right? So NP is a larger class of problems where only verification is easy, right? If you can solve the problem easily, verification is not going to help you, right? Okay, that's the point you need to understand. NP means that there is an efficient certifier, right? It's a weaker requirement, right? It has a problem is in NP if somebody can convince you efficiently, right? If the problem is in P, I don't need anybody's help. I'll solve the problem using my own algorithm. I don't need any proof, right? Okay, so you can do it formally, right? If a problem is in P, then the verifier doesn't even look for a proof, right? Given an instance, it just solves the problem and then says yes or no, right? It can correctly decide efficiently, right? Yes or no, right? Agreed? I think, I'm not seeing a good understanding of NP yet, right? But it's something that, but I hope the puzzle analogy is useful, right? If I can solve the puzzle efficiently by myself, then it's all in P, right? I'm saying let's look at a larger class of puzzles which have the property that I don't have an efficient algorithm for them. I don't know if they have an efficient algorithm for them. At least they have the property, the minimal property, that there is an easy solution, a short solution for that puzzle if there is yes, and there is an algorithm which is efficient and can verify the solution if it is given the solution. That's clearly a larger class of puzzles, right? Yeah? Okay. Puzzles I can solve efficiently by myself, puzzles where I can verify the solution efficiently by myself, even though I cannot figure out the solution by myself. Yeah? Yeah, that makes sense? Yeah? Okay. NP is in P, okay. P is in NP. Okay, what other property does it have? Being in NP implies that it's an exponential time. So what is exponential time? Well, a problem is in exp if it can be solved in time exponential in the size of the input. Okay? Is that an easy definition? Yeah? Okay. Exp is a set of all problems I can solve in exponential time. Okay? Okay, are undecidable problems in exponential time? Okay, good. All right. Okay. So okay, you can take any, it's 2 to the some polynomial, right? 2 to the n, okay. Okay, so I want to say that every problem in NP has an exponential time algorithm. Why is that? Why does every problem in NP have an exponential time algorithm? I will remove the proof to see. Yeah, okay. So why is SAT in exponential time? Let's take examples, right? Why is Sudoku in exponential time, right? Or any. Why the number of solutions is small, right? Exponential. Why? Why is the number of solutions only exponential? Sorry? So, I mean, okay, for Sudoku it's clear, right? It's at most the size of the table and stuff, right? Times exponential in that, right? But I'm saying then, let's think more abstractly of the NP problems, right? The reason why we only need to check exponential number of solutions is because if we know the property that if the answer is yes, the size, there is a proof of size polynomial in the original input size, right? Okay, so that means that we only need to try all possible proofs of length which are polynomial in the original input size, right? And so that's exponential in that input size, yeah? And for every such proof, we give it to the verifier, and if the verifier says yes to all of them, any of them, we say yes. If it says no to all of them, we say no, right? We are guaranteed that it's a correct algorithm. And how long does it take? The number of proofs we have to enumerate is exponential. For each one of them, we have an efficient verifier, right? And we run the verifier on all of them, and if any of them say yes, any proof convinces the verifier, we know the answer is yes. If or all the proofs the answer is no, we know the answer is no, right? In the case of SAT, what are the proofs? Assignments to the variables, right? We know the length by knowing that the size of the string of assignments is at most polynomial in the size of the formula. We immediately realize that the number of such different proofs is only exponential in the original formula size. And we can try all of them, right? For any concrete problem, it is easy to see that, for Sudoku or SAT or, vertex cover or independent set, it's trivial to see that that there is a exponential time algorithm. But if you want to argue formally about why does every NP problem have an exponential time algorithm, you have to actually use the definition of NP using certifiers, okay? Okay. So every NP problem has an exponential time, right? Try all possibilities, right? That is really the algorithm. So what do we know? We have this interesting class of problems called NP. All P is in NP, that means all efficiently solvable problems are in NP, and NP is in exponential time, okay? What would we like to know as both, for practical purposes and as theoreticians, we would like to know what is the truth, right? What does it mean? What is the truth? Is it the case that we are simply being dumb and not being able to solve these NP problems? Or is it really the case that, NP is really hard? There are problems in NP which we don't have polynomial time algorithms for, right? You would like to know, right? Is there an efficient algorithm for these NP problems, or is there no efficient algorithm for these NP problems? Unfortunately, we don't know the answer, right? We would like to know, but we don't know the answer, right? So, big question, right? Is there a problem in NP that does not belong to P? Right? Is P equal to NP? We don't know the answer. Okay, and that's one of the the main open problem in theoretical computer science, and not just in theoretical computer science. It has major implications in all of sciences. So let's see what happens if P equal to NP. Okay? Right? Let's understand what are the implications of P equal to NP. Okay, you can solve independent set, you can solve vertex cover, you can do all kinds of nice things, right? Okay, but you can also do other funky things. You can break your current SSH protocols, right? You can break all your crypto systems. Okay, we won't have any crypto. Current crypto will fade, right? Okay, so that's an unintended consequence of P equal to NP, right? That we are relying today for our security on what? On the hardness of factoring, right? Which is what the RSA is built upon, right? Okay, factoring is a funny problem. That's a long story, right? Factoring is not believed to be a hard problem, even though we don't have an efficient algorithm. Factoring is, people believe that NSA has already cracked factoring and stuff like that, right? So there are other, people still use factoring because there's a lot of efficiency involved in building up the machinery for factoring. But people have other candidates, elliptic curve cryptography and lattice-based cryptography, other ways of doing cryptography, right? All of those will be broken if P equal to NP. Okay, because you can just try, find efficient algorithms to break them, right? Okay, well, what do we do then? Well, we have to think maybe quantum, but so basically you'll have other things, right? Okay. So I'm saying, P equal to NP is a very interesting problem, not just because it's some esoteric theoreticians who care about it, okay? It's something very fundamental to how we actually work on day-to-day life, right? So that's this is a less obvious thing. But if P equal to NP, you can just we can't give you any homework anymore. Okay. If P equal to NP, you can buy a homework solver, right, and just feed your homework problems to that solver. It will efficiently find the solution if there is one. Okay. Then we're out of business, right? Okay. So now this may not be obvious, but it is actually a very simple implication. If P equal to NP, there is an algorithm which efficiently finds solutions for all simple things that we give you. Okay. Okay. That's also bad, I think. Okay. But anyway, okay. Anyway, so what is the current status? Most people think P is not equal to NP. Right? Why? Well, it is because people tried many things. Maybe that's not convincing, but you can win $1 million if you solve this. Okay, that doesn't seem like a lot for this fundamental problem, but it's one of the. This is the Clay Foundation has this list of top mathematics problems that need to be solved. Right? Some of you may be familiar with the Riemann hypothesis, right, which has been an open problem in math for at least 2 centuries, right? And there are many other important math problems, something like 10, and P versus NP is one of them, right? So it's not important just for computer science. It actually has many implications for math and physics and so on. So it's important, even though it's a very simple concept at some level. Okay, so that's some philosophy. Let's look at something that you need to do for your final, right? NP-Completeness. So let's see what is it that we want to get to, right? So okay, now P is contained in NP, and NP has some lot of problems, right? It contains P and many other problems, right? So we want to ask this question, right? And whether it makes sense or not, we'll figure out. Is there something which is the hardest problem in this class? This core problem that, it's not just some problem in NP, but this is a fundamental problem in NP. Okay, how do we define what is this? A really important problem in NP, right? Not just like it's in NP, right? So, the first question is, how do we define it? What does this core problem mean, right? Well, it should be in the class, right? It should be in the class. Second thing is, what is our notion that it's a core problem? One notion is that, oh, look, it's so important that if you can actually solve it, everything in this whole class can be solved efficiently. That would be one possible definition, right? Okay. So what is the hardest problem in a class? Well, it's the hardest problem in a class if you solve this, everything in the class can be solved. Yeah, that's like a reasonable definition, right? Okay. So first, that's fine, but it's not necessary to have such a problem at all, right? For example, what is the largest integer? Okay, right? The set is unbounded. There is no such thing, right? Yeah, right. You keep going, right? So there is necessarily no a priori reason to. Okay, so let's formalize this. What does it mean that if we can solve this, we can solve every problem? We'll call a problem complete or NP-complete if first it is in the class NP, and for every problem in NP, y reduces in polynomial time to x. Okay, what does it mean? That is, X is supposed to be a hardest problem if every problem in NP can be reduced to it in polynomial time to this problem. Okay, this important is for any Y. Okay, does that make sense? What is the implication of this? The implication of this is that if you solve this in polynomial time, every problem in NP can be solved in polynomial time, right? That makes sense? Yeah? Yeah? Okay, so important is for any problem in NP, there should be a reduction from that problem to X. Efficient reduction, not any reduction, polynomial time reduction. So if there is a polynomial time algorithm for X, it means Y also has a polynomial time algorithm, right? Yeah? And because it's for any, everything in NP will have a polynomial time algorithm. So this is what it says. Suppose there is such a problem, suppose there is an NP-complete problem, then X can be solved in polynomial time if and only if P equal to NP, right? If it can solve in polynomial time, everything can be solved in polynomial time and NP will become equal to P, right? Alright? And only if, right? Because if it cannot be solved in polynomial time, then clearly P is not equal to NP, right? Okay? So this is a notion that this is a very hard problem. If you can solve it, that's it. You can solve everything in NP, right? Okay? So it's not clear, how you would even assume that there is such a problem, and how can you even prove this, right? Okay, so but okay, that is what. So what is the consequence of proving that some problem is NP complete? If X is NP complete, if you believe P is not equal to NP, then it means that this problem does not admit a polynomial time algorithm. Unless P equal to NP, you cannot solve this in polynomial time, right? Because if you solve it in polynomial time, everything will be in NP will be P. Okay, so it is evidence that this problem cannot be solved in polynomial time unless something bad happens, or good or bad, it depends on your choice, right, of how you want to think about it. But anyway, it's not going to be easy. So at the very least, this will have a lot of implications, and so you might as well either you persist in thinking that you can make $1 million on solving this problem, or you can do other productive things, right? So that's the way to think about it, right? Okay. Okay. I mean, you have to be careful, right? Just because a lot of people believe that P is not equal to NP doesn't mean you have to buy it, right? You have to use your bias on that. Okay. Now the first thing you have to ask is, are there any problems that are NP complete, right? Is there any problems NP complete? And indeed, the first problem that was shown to be NP complete is SAT. Okay. This was shown by Steve Cook and here in the US, and Leonard Levin at that point in the USSR, roughly at the same time, and SAT is NP complete. Okay. In fact, the proof is actually not very hard if you use the definition of NP completeness using Turing machines and stuff. I used to do the proof, but skipping it now. If you're interested, you can read it. Okay. So let me say a couple of words on why it is a little tricky to prove this. So remember, what should we do to prove that something is NP complete? The definition of NP completeness is every problem in NP should be reducible to this problem, right? See, if I give you SAT and I give you some other problem, I can say, oh look, I can reduce this problem to SAT, right? Yeah, that's easy, that's not hard, right? Because I know this problem, I know SAT, right? I can say, how can I cast this problem as SAT, right? Okay, but this says, for every problem in NP, right? How will you, because there are infinitely many problems in NP, right? I can't prove what A, B, C, D, E, right? So the proof strategy requires a meta proof, right? Yeah. If I want to prove for every problem why it should reduce to SAT, I have to use a proof strategy which uses the characterization of NP in a slightly different way. That's the important thing I want to convey to you, right? That because you have to do it simultaneously for all problems without knowing the problem. Okay? Okay. What does it mean? That means I have to use the characterization of NP using the certifiers, right? What are certifiers? They are programs. Okay, so you have to use really the Turing machine model, and it's going to be a meta proof rather than a concrete proof. Okay, and because of that, the proof, in fact, the details of the proof are not difficult once you understand what is being done. But getting to this meta level requires some thinking, right? You know, what is being asked? So it's a little tricky for that reason, and that's the reason why the first problem that Steve Cook and Leonard Levin use is SAT. Why is SAT good for meta reductions? Because SAT is like a programming language itself, right? Because it's logic as opposed to concrete. SAT is the natural way of expressing a meta reduction. Okay, maybe if that's not clear, it's okay, but that's the reason why SAT was used to prove this theorem and not like some other thing, right? Okay, but they did prove it. They won the Turing Award for it. Great, right? We have the result, right? Now, what does it do for us, right? It shows that there is one problem which is NP-complete. Okay, but once you have the seed problem, it's great. Why? Why is that great, right? Yeah, if you reduce SAT to our problem, then we immediately get that our problem is NP-complete because by transitivity of reductions, right? So that's great, right? You know, once you have this result, then it's very easy, right? If I have my own problem X and I worked very hard, I tried to find algorithms, I didn't succeed, you know, and my boss is asking me, why haven't you come up with a polynomial time algorithm? And you know, what do, right? Okay, you can prove it's NP-complete if it is indeed NP-complete, right? And then you can say, see, you know, other people didn't solve it, so I don't have to solve it, right? Okay, that's one way of making sure you don't lose your job, right? So, okay, but how do you prove that it can be complete? Okay, now you have SAT, you can reduce SAT to your problem. You don't have to go for all, you can just take the concrete problem SAT and reduce it to your problem. Okay, so if you solve your problem in polynomial time, SAT can be solved in polynomial time, but that's NP-complete, which means that everything in NP can be solved in polynomial time. Okay, so once I have my problem is NP-complete, I can give it to my friend, and my friend can use that to prove that something else is NP-complete, right? Because you can start with any NP-complete problem, right? You don't have to start with SAT. Once you know that some other problem is NP-complete, you can use that too, right? So that's very nice. So that's what right? You know, so that's let's see, right? SAT is NP-complete, and we already saw that SAT reduces to 3 SAT efficiently, right? Yeah. So 3 SAT is also NP-complete, right? Yeah. And we'll see that a lot of problems are NP-complete by using this transitivity of reductions. All right. Okay. So that's the plan. So if you have a favorite problem that you want to solve, but you couldn't solve, you can prove it's NP-complete by taking an existing NP-complete problem from the list that people have been compiling over many years, right? And choose the one which is the most easiest for you to think about and reduce that problem to your problem. Okay, be very careful. You have to reduce an existing hard problem to your problem to prove that your problem is hard. Okay, you shouldn't reduce your problem to an existing problem. That would not tell us anything, right? Okay, it's very important to reduce existing hard problem to your problem. Okay, what does that mean? That if you have an algorithm for your problem, that means I can solve an existing hard problem. Okay, okay. Now, so Cook and Levin prove that SAT is NP-complete. Okay, so that was one important event in computational complexity, right? Then the second important event that happened in the 70s is that Richard Karp at Berkeley showed that all these strange looking problems are also NP-complete. And it was not easy to prove them. Okay, so he showed that a lot of natural combinatorial optimization problems are NP-complete by using reductions from SAT, and these reductions are amazingly clever. Okay, and we'll see some of those reductions, right? In the today and next lecture, you'll see these fancy reductions that Karp came up with in the 70s. And once those reductions happen, people realize that, oh, this is a very common phenomenon, that a lot of problems that we think are easy are actually hard in the worst case. We don't know how to solve them, right? And these reductions are extremely clever, okay? Why are they clever? And we'll see, you know, and I hope you agree with me that they're very clever. By now we have a huge catalog of problems, and it's very common phenomenon, right? And the reductions are very clever. Okay, so what I'm going to do now is to prove to you that the independent set problem is NP-complete. Okay, what is the independent set problem? Given a graph and an integer k, does it have an independent set of size k? How am I going to prove it's a hard problem? I'm going to reduce 3 SAT to it. Okay, so this is why these reductions are very clever. It is very odd at the first glance to think that you can reduce SAT to independent set. Okay, think about it, right? How would you reduce satisfiability which has formulas and variables to independent set? It seems not so obvious, right? They're not so related to each other, right? Syntactically, one is coming from logic and one seems like a graph problem which you can have a heuristic for. They don't seem related to each other, okay? But what we'll see is that if you can solve independent set, you can solve SAT, okay? Which is a very clever reduction, and that is these reductions are interesting because they relate problems which seem on the face of it very different, okay? And so that's why it is, right? Okay, remember what is independent set? Graph k. The question is, does this graph have an independent set of size k? What is 3 SAT? A formula, CNF formula with 3 literals with the additional restriction that there are only 3 literals per clause. So what does it mean when I say I want to reduce 3 SAT to independent set? What does the reduction have to do? I want to reduce 3 SAT to independent set. What does that mean? What is the input to the reduction? What is the reduction first of all? It is a algorithm, okay? It's a type of algorithm, right? What does the reduction do? When I say reduce A to B, what are we trying to do? Yeah? Right? Yeah, exactly, right. So what does it mean here? The input to the reduction is a 3 SAT formula. What should I spit out? The reduction should spit out what? Graph and k, right? And what should the property be? The formula is satisfiable if and only if the graph and k that we spit out has a property that the graph has an independent subset as k. Yeah? Is that clear? So we are transforming a formula into a graph, right? And an integer k. Yeah? Agreed? Yeah? That's why it's a little hard to see what, right? Okay. Okay. Moreover, the reduction should be efficient, right? What does it mean? That means the size of the graph we construct, the graph should be, the reduction algorithm should be efficient. It should not take exponential time to create this graph. Otherwise, you can solve SAT itself, right? Okay, that's also important. Okay. Okay. So how do we do that? It seems odd, right? But we'll see, right? Okay, let me just do the construction, right? So by a figure, this is Karp's reduction, which is very clever. So here is the formula, right? 3 SAT formula. I'm going to create a graph out of it. Okay? How am I going to create a graph out of it? For each clause, I create 3 vertices. Yeah? Alright? So this is clause 1, clause 2, clause 3. So I created 3 here, 3 here, 3 here. And I put the literal as a label for that graph, just for our understanding. Yeah? Is the first step clear? Right? So how many vertices did I create here? If there are m clauses here, how many vertices did I create? 3m, right? Yeah? Great. That was easy. Then I make them triangles. Okay? Okay? So far so good? Easy? Yeah? Alright, the next step. I add an edge. If this says x2 and that says not x2, I add an edge between them. Okay? Right? So not x1, 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 not x1, right? x2, not x2, not x2. Yeah? Is this clear, the construction? Yeah? Yeah? So what did we do? For each clause, we created a triangle. Yeah, because they're exactly 3, right? Yeah? And we labeled those 3 arbitrarily, but look, this is not x2, x1, right? Yeah? right? And then, we make sure that we add between vertices of different triangles, we add an edge if they correspond to a same variable, but one is a negation of the other, right? Yeah? Is the construction clear? Easy, right? Okay. Now, this is the graph, okay? So, we've taken a formula and we've spit out a graph, right? But I also have to tell you the K, right? Okay, the K here is the number of clauses. If this K here is 3 because there are 3 clauses. If there are 5 clauses, then my K would be 5. Okay? What is the meaning of this? Okay? The meaning of this, I want to convince you, is that this formula is satisfiable if and only if these graphs have an independent set of size m, where m is the number of clauses in the formula. Is that clear? Yeah? Okay. Do you want to think a couple of minutes as to why you may believe that? Okay, so let me restate what I'm saying, right? I created a graph for you. You see that it is simple graph construction, right? Not very hard to understand the graph construction. But the important thing is to understand that this formula is satisfiable if and only if this graph has an independent set of size at least m, where m is the number of clauses. Okay. Okay. What is the largest independent set this graph can have? Yeah, I mean in general. M, right? Why? Because you can take only one vertex from each of these triangles, right? You can't take 2 vertices from the same triangle, right? Yeah? Is that clear? Yeah? So you can take at most one guy from each triangle in your independent set, right? Okay? Alright? So you can't get independent set of size more than m in this graph, right? But I'm claiming that you can get m if this formula is satisfiable, and you cannot get m if it is not satisfiable. Okay? Okay, how can you get m if the formula is satisfiable? Is this formula satisfiable? Yeah? Okay, how can you get m in this case? Okay, what does it mean this formula is satisfiable? That means that there is an assignment to the variables such that all the clauses are true, right? Yeah? Instead of thinking of it that way, let's think of it another way. There is an assignment to the formula such that in each clause, I can point to that guy, one literal, and say, that guy is the one which made me true. Yeah? Okay? So fix an assignment to this, which satisfies that formula. Give me an assignment. Sorry? Okay, let me see. So I can say, okay, x. What is this? Why is it drawing this? Okay. Okay, so we can say x1 is false, x2 is false, okay, x3 is, x4 is whatever, matter, true, you want to put true? Okay, alright, so why is the formula satisfied? Okay, can you tell me, give me one literal in each clause that satisfies it? x3, x3 and x4, right? Okay, those are okay, right? Okay, now I'll say, okay, look, take this vertex, takes this vertex, take this vertex. I claim that should be an independent set. Why? I mean, why is it not an independent set? Only if there's an edge between them, right? Because remember, they're in different triangles. Will I have an edge between them? What does it mean that they have an edge between them? They can have an edge between them if and only if one is a negation of the other, right? But if one is a negation of the other, I would not have picked both of them, right? Because this satisfied this. I can't, if I have an assignment, it's either true or false, right? I can't make, x3, if it, I could not have picked, for example, this is not a good example here, but I could not have picked not x1 here, and sorry, x2 and not x2, right? Both of them I could not have picked, because whatever fixed assignment I have, if this satisfied this, this cannot satisfy this clause, right? So these three vertices must form an independent set. So if there is a satisfying assignment, I can pick one vertex from each triangle such that they will give me an independent set. Yeah? Agreed? Questions on that? That seems okay? Yeah. But the converse must be also is a difficult direction. What do I need to convince you? That if this graph does have an independent set of size m, then the formula is satisfiable, right? Okay. Okay. How can this graph have an independent set of size m? Let's take any independent set of size m in this graph. I have to give you a satisfying assignment from that for the formula. Can you think of how to do that? If I give you an independent set of size 3 in this graph, you should be able to create a satisfying assignment for the formula. How will you do that? Yeah? Exactly, right? If I give you 3 vertices, 1 per each triangle, okay? I mean, remember, if I have a size of independent set of size m, it must be exactly 1 from each triangle, right? There is no other way to get m, right? I can't take more than 1 from each triangle. So if I have an independent set of size m, it must be that every triangle has 1 vertex in my independent set, right? So how will I get a truth assignment from that? I say, okay, look, if this was the vertex, I say, aha, this must satisfy this clause. To make this satisfy this clause, I should set x1 to be false, right? Okay. So if it gave me this, and that, I'll say x1 should be false, x2 should be false, and x1 should be false, right? Okay. That will definitely satisfy the formula, but if I run into, when I run into a problem as I'm going around, if suppose, I chose x1, not x1 here, suppose, I chose x2 here, then I should make it true, but maybe I come here and I chose not x2, but could that be possible in my independent set? No, because there was an edge, right? So that was not a valid independent set. So if you give me 3 vertices which form an independent set, I can give you a truth assignment by making that literal true, and that will satisfy that clause, and I will not run into any problem, because I will never run into the problem of trying to set the same variable true in one triangle and the same variable false in another triangle, because they would have an edge and they would not be in the independent set. Yeah? Agreed? Okay, that's it. That's the reduction. It's efficient, right? It's a simple construction. And I convince you that the formula is satisfiable if and only if the graph has an independent set of size m, right? So if you can solve independent set, you can solve satisfiability. Yeah? Okay. That was Karp's clever reduction, right? Right? Okay, in retrospect, it's easy to verify this, no? Yeah? But can you come up with it? It's different, right? So that is what NP, when I said, solving homework, right? Is like, this is a very clever reduction, but we can understand the reduction, right? But coming up with and it's also short, right? The proof is short too. But coming up with the construction is hard, right? That's what we intuitively believe. That's why people believe P is not equal to NP, that the fact that we can check something clever doesn't mean that we can be clever and construct it, right? So that's the P versus NP question, right? P versus NP question in layman's terms is creativity automatable, okay? What does that mean? That, can people, just because we can understand a creative solution, does it mean that it can be done also efficiently, right? We kind of intuitively think it's not, but we don't have a proof, okay? That's the thing. Okay, any questions on the construction? Yeah? So the mechanics of the construction are okay. To prove that, independent set is NP complete, we took an existing hard problem. What is the existing hard problem? SAT, right? Or in fact, 3 SAT, right? and we converted it into our independent set problem, right? So who told us 3 sat is hard? Cook-Levin told us 3 sat is hard, right? Okay, so that's a seed problem, right? And once you have more problems, you can. So now I claim that vertex cover is hard, right? Why is vertex cover hard? Yeah. Yeah, last lecture we reduced independent set to vertex cover, right? So we already did that, okay? And so vertex cover is hard. We reduced clique to independent set. So sorry, independent set to clique. So clique is hard, okay? All right. So we can do more and more, and those are easy reductions, right? Those were not hard reductions. I mean, sorry. This was a clever reduction, right? Yeah. Okay. So now, what I want to mention to you is 2 more problems that we'll see are hard next lecture. But I want to define those problems so that you can use them in your reductions without even seeing the proof, right? You see, you don't need to know the proof that the independent set is hard to use the hardness of independent set for your own problem, right? So you need to know a bunch of problems are hard, and I'll do the formal proof next lecture. But let me tell you the 2 other problems which are going to do next lecture. One is the Hamiltonian cycle, and the 3-color problem in circuit sat is really sad. So you can you'll see. Okay, what is the Hamiltonian cycle problem? Okay, so the Hamiltonian cycle problem is the following, right? I give you a directed graph, and I want a cycle which visits everybody and comes back to the start. Okay, so this is the Hamiltonian cycle problem, right? It's a long cycle, right? It's a cycle, it shouldn't visit the same vertex more than once. So the question is, I give you a graph, a directed graph, and the question is, does it have a Hamiltonian cycle? Okay, a cycle which visits all the vertices. Is the problem clear? Yeah? Yes? Okay, I can ask this in directed graphs, and also ask this in undirected graphs. And it's one of the nice problems where, you know, the directed graph problem can be reduced to the undirected graph problem. The other way is easy, right? Reducing the undirected graph problem to the directed graph problem is easy. You bidirect the edges. But in this case, you can reduce the directed graph problem to the undirected graph problem. Yes. So which means that the undirected graph problem is hard. Okay. So it's a very nice problem, very cute problem, connected to the traveling salesman problem and so on. What do you think? Does this graph have a Hamiltonian cycle? Yeah. Yes? Don't be so fast, right? You know. How do you know? See, it has a feature that if it has a Hamiltonian cycle, I can convince you, right? I can show you the cycle and you'll say, ah, yes, yes, yes. But suppose it doesn't have a Hamiltonian cycle. It's hard, no, to know, convince, right? So NP is asymmetric, right? NP is not closed in the complement, or at least we don't know that, right? If I want to convince it doesn't have a Hamiltonian cycle, it's very hard for me. Okay? Right? Or it's not, I mean, from this picture, it's not even clear it has a Hamiltonian cycle or not, right? Okay, you can do it later, okay? I'll show you one more problem that we'll see. This is a clever reduction that Karp came up with. The idea is to see them and say, wow, and then say, okay, graph coloring. Okay, what is graph coloring? Graph coloring is another very basic and important problem that models many situations. It is kind of related to the independent set problem, right? So I give a graph, and I say, for example, it is 3 coloring, right? I want to color the vertices with, say, 3 colors, such that for any edge, the 2 endpoints have different colors. Okay? Okay, why is this interesting? Suppose, you know, I want to schedule some lectures in a classroom, right? So any kind of such situation, right? You know, where I have a graph which represents the property that if there's an edge between 2 vertices, that means there's a conflict between them, right? I cannot schedule this and this at the same time. Okay? And so coloring is a way of taking this graph and partitioning the vertices into different color classes, such that within each color class there are no conflicts. Okay? So here is a way to color this using 3 colors, right? Does it make sense? Yeah? So for example, these two, right, this is, can you do it with two colors? Why not? So you have a triangle here, right? You can't color this triangle with two colors, right? Okay. So you need three colors for this. Okay. So okay, suppose I ask the color, can you color a graph with one color? What does that graph look like? No edges, right? Empty graph. Okay. What about two colors? Sorry? No triangles is not enough. Suppose I give you a pentagon. Can you color a pentagon with two colors? Odd cycles cannot be colored with two colors, right? Yeah? If you have odd cycle, take pentagon, right? If you have a pentagon, you cannot color it with two colors. You can say, how do you figure that out? You start with, say, color 1, then you have to color 2, 3, okay, 1, you have only two colors, so you keep going, there's no choice, and you'll get stuck because it's a odd cycle. So the question is, when can a graph be colored with two colors? Yeah? Yeah, why is that? If a graph can be colored with two colors, what does it mean? Take color 1 vertices. They must form an independent set, right? Yeah? Color 2 vertices must form an independent set, right? So a graph can be colored with k colors if and only if it can be partitioned as a k-partite graph. So two colors is bipartite graph, right? A and B, where there's no edges between A and no edges inside A and no edges inside B. Okay? Can you check whether a graph is bipartite efficiently? We did. It's in the notes. Okay? So you can use BFS to check whether a graph is bipartite in linear time. Okay? Linear time, very efficient, right? While with three colors, it becomes NP-complete. Okay? Right? So that's the coloring problem. What is the coloring problem? Given a graph, an integer k, can you color the graph with k colors? Okay? Even when k equal to 3, it's NP-complete. Okay? K equal to 1 is trivial, k equal to 2 is interesting. Bipartite graphs, you can do it in linear time using breadth first search or other methods, right? While k equal to 3 is NP-complete. Okay? And it's a very clever construction. It's one of my favorite. We'll see it next. Okay? All right? Okay.